On this slide, we want to talk about excision. You can find this on page 119 of Hatcher. So the idea is this. Sometimes we are given a big space X and a subspace A of X, and we want to excise out a small space Z from space A so that the homology computations are easier. So let us see the theorem. So you have this big space X, it has subspace A, and which in turn contains the space Z. So you have the inclusions. Z is contained in A is contained in X. In particular, closure of Z is completely contained within interior of A. Now we have natural inclusion maps of the pairs X minus Z comma A minus Z, which is included into X comma A. Now this induces the isomorphism in the corresponding homology groups. So Hn X minus Z comma A minus Z is isomorphic to Hn X comma A for all n. Now another variant of this theorem is you set X minus Z as B, and this would immediately imply that A intersection B is A minus Z and A union B is X. You can see this in a diagram here. So A and B cover X. So you have X, you have a subspace A, you have a subspace Z. So now shade B as X minus Z. So the shaded portion is B, which is X minus Z. So you can now see A intersection B is A minus Z and A and B cover X. So now we just copy down the induced isomorphism of homology groups. So we Hn X minus Z is B, A minus Z is A intersection B, and you keep X and A as such. So now it is time for an example. So this is an important example. It will be used later on. So you say the space X is Rn and space A is Rn minus this point X in the space Rn. So you fix B as the neighborhood of point X. So B is some set U which is neighborhood of point X. So big space Rn, small point X, and U is the neighborhood. Okay, now A intersection B is U minus X. Now we just have the isomorphism of homology groups B comma A intersection B, which is U comma U minus X, Hn X comma A, which is Rn comma Rn minus X. So in particular, you notice that these homology groups depend upon the local topology of X near this point X of space. Now let us talk about a proposition. So we want to discuss the proof of a proposition. This you can find on page 124 of Hatcher. So you start with a good pair X comma A. So that means A is a deformation retract of some neighborhood of X. So you have a quotient map going from X comma A to X by A comma A by A. So you notice that Q restricts to homeomorphisms on the complement of A. So Q restricts to homeomorphisms on the complement of A. Now this quotient map will induce isomorphisms. In the corresponding homology groups. So you have a quotient map and that gives you isomorphisms in the homology groups. So let us write down the proof. So what you do first is you fix a neighborhood V of A such that V deformation retracts into A. So you have this pair V comma A, which is homotopically equivalent to A comma A. So that means the homology groups are isomorphic, but Hn A comma A is 0. Yeah, so you have A relative to A, so you have 0 by definition of these relative homology groups. So now we want to draw a commutative diagram which will end up proving this proposition. So first we draw this map Hn x minus A comma V minus A, and then Hn x by A minus A by A comma V by A minus A by A. Now the map between these two homology groups is induced by the quotient map, and since this quotient map restricts to homeomorphism on the complement of A, and this map now we have on x minus A and V minus A, so we have on the complement of A, and it is a homeomorphism on the complement of A, so we have a iso. Now we want to use excision, so we are throwing out A, and by excision we have the isomorphism. So the top arrow and this bottom arrow are both by excision, they are iso. Now this arrow from Hn x comma V to Hn x by A comma V by A, so we have an arrow here that is induced by the quotient map, but this arrow is a iso now because what we have is a commutative diagram and other three arrows are iso. So this fourth arrow induced by the quotient map also has to be an iso. So now let us talk about a long exact sequence of this pair XVA. So we have a triple x comma V comma A. So we want to talk about its long exact sequence. So you have Hn V comma A to Hn x comma A to Hn x comma V to Hn minus 1 V comma A. Now we have already seen before this Hn V comma A is 0. This is 0 for all n. This is 0. Here also it is 0. So we have isomorphism here. So let us note this isomorphism. So we have isomorphism here. Now we will take another long exact sequence of a triple x by A comma V by A comma A by A. So I'm just copying the same map which I had above below, but replacing everything by modulo A. To Hn minus 1 V by A comma A by A, and so on. So again this will be 0, this will be 0. So you can say this is a long exact sequence of a triple x by A comma V by A comma A by A. So now we have obtained this isomorphism here. Let us record it. So we have a isomorphism here. So now we see that there are 3 arrows which are iso. So the 4th arrow will also be iso, and we have this 4th arrow from hn x comma a to hn x by a comma a by a because it is induced by the quotient map. In fact, all these 3 arrows which I have ticked in red are induced by the quotient map, and we are done.